American Sign Language is inherently dynamic. Capturing that fluidity in an educational application presents an immediate, unique challenge. SignWell is a Next.js 14 app router application designed to teach ASL through visual-first design and structured repetition. The platform centers on two primary interfaces: a server-rendered visual dictionary for looking up signs, and a real-time fingerspelling trainer that tests both spelling accuracy and reception speed. Teaching a spatial language requires dense media. Every individual sign relies on multi-angle video context, front, side, and sentence usage, paired with specific grammar notes and non-manual markers like facial expressions. This creates a severe architectural tension. A highly interactive, media-heavy client interface must constantly synchronize with a strictly controlled, data-intensive backend that calculates learning progress. This architecture map shows the baseline solution. The stack relies on Next.js to route data from the client layer into a neon Postgres database, while integrating Clerk for authentication and Stripe for subscription management. The core learning mechanism is a spaced repetition system based on the SM2 algorithm. This system calculates review intervals for every single sign a user learns, generating a massive volume of database operations as the active user base grows. Delivering this scale requires moving past basic CRUD operations. It demands strict fail-fast startup protocols, highly optimized database algorithms, and resilient webhook idempotency to handle unpredictable external networks. A flawless, engaging user experience is not the natural state of web software. It is an illusion maintained entirely by rigid, defensive back-end engineering. Resilience starts before a user ever loads the page. A system cannot be trusted if it begins accepting HTTP requests in a broken state. SignWell enforces this through a dedicated validation file, src/lib/env.ts, which verifies all environment variables the exact moment the application module loads. It uses Zod to partition configurations into two distinct schemas: a client env for public keys and a highly restricted server env for sensitive database strings and API secrets. The application wraps the server variables in a proxy. If client-side code attempts to access an unvalidated server secret, the proxy instantly throws an error, halting the operation. Imagine a deployment where the Stripe key is missing. The server boot process suddenly halts. Traditional configurations might silently boot, leaving errors for production. SignWell intentionally crashes, outputting a consolidated list of every problem. Once the keys are validated, the pipeline clears. If a system boots without a required key, the downstream effects corrupt the data layer. Users might register successfully, but the missing secret prevents the Stripe webhooks from firing, leaving their billing profiles permanently out of sync. By catching these omissions during initialization, engineers avoid debugging obscure data inconsistencies at 3 in the morning. Abruptly crashing an application on startup is infinitely safer and cheaper than allowing a misconfigured state to silently corrupt production data. Down at the Postgres data layer, the user-sign progress table acts as the engine for the platform's learning mechanics. Here, SignWell implements the SM2 spaced repetition algorithm. It tracks the exact memory state of every vocabulary item for every active user. Because visual learning has unique cognitive demands, the algorithm includes custom receptive difficulty weighting, which mathematically modifies how intervals grow and decay over time. When a user reviews 20 signs, saving results one by one hammers the database with sequential calls. SignWell bundles the batch into a single SQL command. Using an insert-on-conflict-do-update, it executes a bulk upsert, adjusting multiple rows simultaneously. Then there is the challenge of streak computation. Tracking consecutive daily logins requires navigating month rollovers, leap years, and gap resets accurately. If a user posts progress from 2 devices simultaneously, sequential read-writes cause one session to overwrite the other streak. To prevent this, the database executes atomic delta updates. The SQL instruction tells the database to perform mathematical addition on the existing column directly. This logic is verified by 34 isolated unit tests that specifically cover interval growth, failure resets, and streak computations to guarantee mathematical certainty. Advanced algorithmic learning features demand heavy computation. If the underlying SQL operations aren't designed to bypass concurrency limits, those features stall out as the user base grows.
Managing an educational platform also means managing access. SignWell enforces 4 distinct billing tiers through Stripe: free, individual, pro, and team. To maintain security across the application, authorization relies on a single source of truth, a has-plan utility function that evaluates the user's current tier against the requested resource. A common vulnerability in front-end development is enforcing access purely through the user interface. Developers hide premium buttons, but leave the underlying API payload completely exposed to anyone inspecting the network tab. SignWell closes this gap with a 2-layer security model. The defense begins at the server component routing layer. When a free user attempts to navigate to a paid lesson, the server component evaluates their tier and actively redirects them before the premium layout ever renders. This diagram shows the second, deeper layer of defense. When a data request hits the /API lessons endpoint, the API route boundary actively strips the paid video metadata from the JSON payload for free users before it travels over the network. This requires careful curriculum routing. Instead of hard-coding sequential lesson IDs, it computes the next lesson based on a module order index. This allows free users to seamlessly bypass locked content and continue learning. Access is also gated by the first-run experience. A layout interceptor halts new users until they define their learning goals and daily time commitments, persisting that state before unlocking the dashboard. True data security in a headless architecture assumes the client is inherently untrustworthy. You protect premium content by stripping unauthorized data at the absolute source. Integrating billing and authentication providers like Stripe or Clerk creates a new attack vector: webhook fragility. It is a misconception that processing webhooks is simply a matter of routing JSON payloads. Distributed architectures are volatile. External services will inevitably fire duplicate events, retry operations aggressively, and deliver messages entirely out of order. If left unmanaged, these race conditions crash systems. A duplicated user-created event triggers a unique constraint violation in the database, or worse, processes a duplicate payment. A single aggressive Stripe retry can cascade, prompting the AWS SES pipeline to fire multiple identical subscription confirmation emails to a single user. To defend against external chaos, SignWell uses claim-based idempotency. The foundation is a webhook events table acting as a central idempotency log for incoming hooks. When an event arrives, the handler fires a single atomic SQL command: insert the event ID. On conflict, it does nothing. The database enforces a binary outcome. If the insert succeeds, the specific handler officially owns the event and proceeds with processing. If the insert fails, it acts as mathematical proof that a parallel thread has already processed that specific event. The handler instantly short-circuits and safely ignores the payload. System integrity cannot rely on trusting external network consistency. It is forced by assuming total failure and enforcing strict rules at the database constraint level. Pulling back from the database constraints reveals the actual value of this architecture. These rigid foundations are exactly what enable a seamless user experience. The strict relational data model directly handles regulatory compliance. Because the database relies on cascading foreign keys, a GDPR Article 17 account deletion requires only a single clean operation. That same unified schema allows the /API/me/export endpoint to instantly generate an accurate JSON payload to satisfy GDPR Article 15 data requests, automatically stripping out internal observability fields. Because data delivery is robust and predictable, the front-end code is free to focus on critical accessibility features. The fingerspelling trainer relies on ARIA-live polite regions to announce individual letters precisely to screen readers. Decoupling core logic allows serverless infrastructure, like automated Vercel cron jobs, to trigger street computations asynchronously. The main application thread is never blocked. Similarly, the email pipeline operates on a best effort audit trail. Milestone emails fire asynchronously, ensuring that background notifications never bottleneck the primary user response path. SignWell functions because it treats its stack as an integrated organism. Its effectiveness as an educational platform is rooted entirely in its holistic synthesis of Next.js, Clerk, Stripe, and Neon Postgres. True production-grade engineering is not the pursuit of writing perfect code.
It is the deliberate design of systems that anticipate, absorb, and neutralize failure before the user ever notices.